Okay, our purpose is to update this, time update this quantity. Remember, what was this quantity? This was the inner product between this and sorry, this is, you know the definition of this. In case you have forgotten, EPNF was P1 Pn perpendicular xn forward projection error vector pth order, and EP n minus 1 B tilde, this is actually P1 Pn perpendicular, same operator, which is actually 0 isn't it? This you remember, right? How the 0 comes? Because all these fellows, the columns of the corresponding matrix and these fellows, they all have 0 at the top, first row. Okay. So, in the sum of square error, that row does not correspond amount to anything. Other rows you add up, and I mean you get the optimal filter coefficient for the pth order backward projection error n minus 1 with index. So, if when you combine the columns, top fellow again becomes this, other fellow becomes a projection, and then they take the error, projection error and all that. Okay. We have to update this, and last time I will just quickly go through. Last time we worked out one relation. What is the relation? That is, suppose there are some columns given U1n dot 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 and pi n. This is one matrix. I don't know, I don't remember what name I gave to it, forget it. Did I give any name to this matrix? U n pi or something, is it? U pi n. And there was another matrix U prime pi n, n minus 1, pi n minus 1, which was this U1 n minus 1 0 UP n minus 1 0 and pi n. And I said, I proved, I will not reprove it again, that the space spanned by the columns are same. There is a column space of the two matrices are same. Therefore, if I have any external vector dn, I want to project it orthogonally on the space spanned by these fellows. Column space, I gave a name, I think w pi n, isn't it? So, if I want to take any vector dn and project it orthogonally on w pi n, I can take this also, the space spanned by these fellows, and project it there. But here pi n is orthogonal to u, sorry, pi n is here. Pi n is orthogonal to each of these columns, because pi n has only one at the end, last element, other element 0, and all these vectors have last element equal to 0. So, inner product is 0. Therefore, the external vector dn you project on the space spanned by these p fellows, compute that and separately project it on pi n, compute that, add the two. That will be the net projection. That way, if you compute, if you take dn, if you linearly combine this u1 n minus 1 0 up to up n minus 1 0, subtract from dn and form sum of squares. Last elements here we are giving rise to what? Zeros, subtracted from dn minus 0 whole square independent of C1 to Cp. So, that does not contribute anything to the sum of squares. I mean, by other terms in the sum of square comes from row number 1 to row number n minus 1. And when you minimize that, you get those optimal filter coefficients which correspond to the optimal filter coefficients at n minus 1th index. That is, if you are giving data dn minus 1, vectors u1 n minus 1 up to u2 up n minus 1, you are finding out that optimal filter coefficient, that is what you will get here. Because in the sum of squares here, last element is dn minus all zeros whole square, that is dn square independent of the coefficients, right. So, with those coefficients, if you now combine these columns, last element will still remain 0, but when you combine them, you will get d cap n minus 1. That is a projection of d n minus 1 on the space spanned by u1 n minus 1 to up n minus 1, isn't it? D cap n minus 1. And when you take dn and project on pi n, you will get a vector with all 0 and last component will be dn itself. Add the two, so you get a vector d cap n minus 1 and then one dn. You have to find out the error vector, projection error vector subtracted from dn. So, last element cancels out because there is common dn here, dn in dn also, and the other half, the top half will become what? dn minus 1 minus d cap n minus 1, which is projection error. Okay, that is p pi n. From one angle, it is d cap n minus 1, sorry, I am taking the error. So, this error will be which error? That is, if you take dn, project it on the space spanned by e1 n minus 1 to ep n minus 1 and take the error, that one. So, p n I said, p n minus 1 perpendicular d n minus 1, right. This is also equal to d n minus 1 minus that d cap n minus 1. Actually, there should be a subscript to indicate the data taken up to n minus 1th index, but you can drop it also, followed by 0, because dn vector last component is scalar dn. This summation, projection on this part and projection on this part, the resulting vector last component is d of n coming from pi n. So, subtract 0. This is what you obtain there, but that is same as projecting dn on the space spanned by these fellows also, because the two spaces are same. Here you can orthogonally decompose this space as the one space by u1 to up. Direct sum, if you take the projection of pi n on the space, take the error, space spanned by that error, and dn, then you project on both, add, and you are finding out that projection error. So, not the projection, but projection error. So, that would give rise to what? Sorry. Are you following this? I am taking u1 to up, dn projected on that and the error. There is nothing but p n perpendicular dn. Projection is p n dn. So, p n perpendicular dn minus because when you compute the error, this will become minus sign will come up. Minus of what? dn inner product with did I use this notation that day? P n, I used the notation P n, isn't it? And here I can swap this P n perpendicular from here on this, okay, which will be d cap n. So, which will be an error, corresponding error, and then the last component of that will come up. So, this is how the projection error vector at nth index and the corresponding vector at n minus 1 index are related. They are not directly, I mean, it is not that this is equal to this, not so simple. You have this additional term. This quantity I told, it is like a angle parameter, it is actually sin square theta. I explained through a diagram, I will not redo it. It is called angle parameter, fine. These are the additional things that are coming up. This I will be putting in this context now. This was what I did, this is a general result, I will be now using it to update delta P n. Okay, what is delta P n? Delta P n is this. I can also write delta P n as put back the results, okay. You can take away this one operator. The two operators are same, you can take away one operator. sorry. Okay. So, let us concentrate on this error vector. This error vector is a vector at nth index. I will relate it to the corresponding vector at n minus 1th index through a formula like this and substitute that here. This one, this dn is here z to the power minus p plus 1 into xn. That is your dn here in this page I am doing now. dn is in this case z to the power minus p plus 1 xn. Okay. And u pi n is what? See the projection operator 1 to p at the nth index. Okay. So, here it was p n perpendicular, here in this context 1 to p. So, that means I will construct this. Finally, dn projected on the space spanned by this, that has to be related to the corresponding thing at n minus 1th index. But that, as this theory shows, this extra term comes up. That is why I started with not u n, but u pi n. In this context, what is u pi n? Okay, you take the columns here. What are the columns? Z inverse x n to Z inverse p x n, like u 1 n to u p n. That is this. But for application of this theory, I need to append pi n also. I need to consider u pi n, not u n. That is why I constructed this matrix. Okay. So, then using this theory, maybe for your sake I redo this in this context. One is u pi n, that is, as I said, Z inverse x n pi n, right? And another is, that is what? Fine. Huh? Pi n. Here I called it pi n minus 1. What is the problem? Pi n u 1 n minus 1. If this u n, I am making it n minus 1 here. Is that fine, Mighty? So, same thing, the space, as you know, I have done it there in the general context. I call them u1 to up. I am just giving the specific forms there, that is all. But the two spaces are same, space spanned by this, and therefore, any external vector. External vector here is dn, as I said, dn is equivalent to Z inverse p plus 1 x n, is not it? So, this dn projected on this space is same as projected on this space, and the errors are same. dn in this case will be what? If you take the projection error, you consider the space spanned by this, take the corresponding error. You project this on this and take the corresponding error. What is that? Are you forgetting this? This component, if you take, is just restating the same thing using this language. This is language of these specific vectors. dn, last component of this minus combiner coefficient times zeros will contribute nothing in the sum of squares. Only previous terms of this vector. Only previous terms will come up, they will give rise to the same linear combiner coefficients, which are the optimal combiner coefficients at n minus 1th index. If you use them and recombine them, you will get what? If you take the last component out, remaining part projected on this space spanned by these fellows. What is last component? If you take out, what is it? and then last guy. Last guy is not any consequence to me. Last guy is x n minus p minus 1. You are agreed to this, no? This form. Z inverse p plus 1 x n. You have so many zeros on top and then x 0, x 1 dot dot x. If you take the last guy out, then you are, this is the nth index. Previous one is n minus 1th index. If you stop here, you are getting as though the x n minus 1 vector is delayed by p plus 1 times, that component and the last component. Are you following? This minus linear combiner coefficient, I mean this into one coefficient, this into one coefficient. When you add last component minus zeros and square up, they contribute nothing. Previous part minus C1 times this, Cp times this, that error vector's norm square is minimized. So, you get those coefficients which result when you take this part and project it orthogonally on the space spanned by these fellows. Now, by those coefficients if you combine them, bottom the last row will contribute 0 and the upper part will contribute what? Yeah, the projection of this fellow on the space spanned by these fellows, Z inverse x n minus 1 to Z inverse p x n minus 1. And on this guy, if you take the thing, only the last component will come. You take the error, last component will disappear. So, this projection in one context, the projection is giving rise to what? Last component went out by subtraction, p 1 p n minus 1 which is E tilde when it was n, you forgot the definition. When it was n, I put the subscript n minus 1, isn't it? Because actually this is the thing, there was a 0 and this is the previous, this is a backward projection here corresponding to previous index. Together I gave it a name, this. Because every time I have to write a vector like this with a 0, to avoid that I gave it a name. This time the projection is not at nth index, but n minus 1th index. Vector not x n, Z inverse p plus 1 x n, but Z inverse p plus 1 x n minus 1 and all that. So, this is this. Okay. On the other hand, if you project that guy on the space spanned by this, you consider this is relatively simple. Consider this one part is this part spanned by this, another part is what is called project pi n on the space spanned by these fellows, take the error, take the span of that. On that you project dn. So, this is one component and then take the error, because I am taking the error here. So, one component will be what? Are you getting me? This fellow you are projecting on this. So, this is this and then taking the error, and there is a minus sign because you take that, it becomes instead of plus, it becomes plus in the projection, in projection error this becomes minus. Minus of what? This guy projected on what? First we project pi n on this and take the error, this on that component. Okay. P1 to Pn is very simple now. Pi n projected on that error. So, this is that error thing. This quantity I will call this angle parameter. This I will call gamma Pn. It is a positive quantity. This is a square. Here, what I will do is very simple. You see, I will take this operator, put it on this. Pi, it will become pi n, I will not show this step, it will become pi n, this operator will sit on this. What will that give rise to? E tilde b p n minus 1, isn't it? That into pi n. E tilde b p n minus 1 means this, into pi n means last guy of this fellow, this vector. And this is your E tilde by definition minus last component of this I should write a subscript comma n minus 1, but as I told you, since always the two subscripts will be same, we drop when you constitute the scalar error component. But always remember, ideally I should put a subscript here with n minus 1, showing that data up to index n minus 1 was considered in finding out this projection error. But just for saving of space and nothing else, I am dropping that index, because I know that the two time indices are same. So, you can always drag this here if you want for some clarification. Okay. Just for saving space and no other reason, I am dropping it here. But this means what? If you take the data up to n minus 1th index and then carry out pth order backward prediction error, the latest backward prediction error component is this. This times gamma p n into this guy. Okay. Which means this fellow is what? LHS plus this much, LHS plus this much. In delta p n, I have to carry out the inner product between the two, and finally this. That is finally between x n and this guy actually. Between x n, either you write in this projection form or this form. You have to do the inner product with x n and this guy. This guy I substitute as LHS plus this much. Okay. So, delta p n this how we make the substitution. LHS, for your sake I am writing in the vector form, this 0 and plus this. Okay. Now, consider these two. Last component of x n and multiplied by 0 will yield nothing. In the other terms, last but one term will be having multiplication factor lambda, previously lambda square, then previous to that lambda cube, like that. Last one 0 into x n, that is free of lambda, but that is 0. Before that lambda, before that lambda square, before that lambda cube. So, you can take lambda common, and if you do that, lambda times it amounts to what? X n minus 1 vector into this plus this is a scalar into x n times that. And if you permit, at this stage only I can pull this operator, put it on x n. You understand? X n times this, and in the next step I take this operator, apply it on x n. This guy is E p n f. So, last component of that easily. Okay. Here this quantity is what? take the operator, apply on this. What will you get? No, if you one step at a time. If you take this operator, apply on this vector, this forward prediction error vector, n minus 1 is the current index. So, it is a current index vector, current data vector projected on what? 1 to p. So, with reference to this current index, delay from index 1 up to delay index p, corresponding data vector span a space, on that I project this vector, take the error. This much only will be taken away, this much applied on this. Okay. And here you see it is just very nice result. EPF, last component of this vector, I can put a subscript n, but again for the same reason I will drop that subscript. But this means actually there is a subscript comma n, that is indicating that data up to nth index has been taken on that error, using that error vector has been computed, last component of that. But again the same index prevails here, so I just drop for saving of space and nothing else. EPFN here, EPB. Please try to understand the difference between the two. Here n and here n minus 1 means here the vector from which it is derived, and here they are belonging to different, they are different in nature, in the sense, though even then they are forward and backward, we are otherwise different. But here it means data up to index n was taken, based on that forward prediction error you perform calculated, last component of that, and here data up to n minus 1th index was taken, based on that forward backward prediction error, pth order was computed, last component of that. Just looking at this, that aspect does not cover. So, how much data was taken in the least squares estimation or projection computation. So, this you should always be there in your mind. Gamma pi n will never be equal to 0. Pi n does not lie in the subspace spanned by those x n up to z inverse p x n minus 1. This quantity is E p n minus 1 f, right, and this inner product is delta p n minus 1. So, this quantity is delta p n minus 1. So, this is a time update relation. For pth stage you already know these two terms, they are coming from the previous stage of the lattice, multiply the two, suppose this is known. So, compute that, add that to this previous value. Find delta p n, using this delta p n and these two errors, find out E p plus 1 f n, E p plus 1 b n. Those two multipliers in the two arms, they are having the values delta p n, they are taking the value on the numerator delta p n. So, first you have to compute this from pth stage error, pth stage error. So, this is an extra term, update term, past value. Get this, using that EPFN and EPBN minus 1, get the corresponding figures for p plus 1th index. Okay. Now, let us try to write down the algorithm and see, but one more thing, yeah, gamma p n. Gamma p n is an irritant. This has come up because we are doing exactly squares minimization, no E operator, no approximation, nothing. So, that is why these extra terms are coming. So, we have to take care of gamma p n. Gamma p n fortunately can be order updated. Delta could not be, and that is why you have to do all this kind of complicated analysis and all. And this is more computation intensive, you need division, multiplication, etc., and this extra term is coming and all that. Order recursion does not require such extra operations or extra variables and all that. Fortunately, gamma p n can be order updated. Let us see what is gamma p n. You also can do. Gamma p n is what? Norm square of, if I am correct, so what is gamma p plus 1 n? That is, norm square means inner product with itself, just instead of p I have to put p plus 1, but I can take I can take away operator from one of the two. Sorry, this is p plus 1, and here I take out the operator. This is jolly simple. What is the subspace here? Space spanned by Z inverse 1 x n to Z inverse p plus 1 x n. Z inverse 1 x n once again you decompose as what? Space spanned by, that is equivalent to W 1 P n I think by now we are familiar with these notations and all. Otherwise, where from this comes? This guy take its projection of the space spanned by this fellow and take the error, but that by my definition is this. So, simply to compute this error, pi n on this, pi n on this and the error. Pi n on this and the error will give rise to minus pi n on this. Pi n is projected on this part, This part is here, the corresponding error, and pi n on this part will remain. We have a norm square. Norm square of this is same as sigma p. We have seen this. The two guys are defined for only this fellow has one 0 on top of E p b n minus 1. That does not change the norm square. So, this times that fellow pi n on this. So, inner product by norm square into this fellow. And comma this pi n. This much is this. This projection is this much, right? Inner product. So, comma pi n. And you can easily see when I take this pi n and this, I will repeat this operator, I will bring it on pi n again. So, it will become norm square, but at pth order. So, that will give rise to gamma p n. Obviously, order update you can see. It is not difficult. After a while, it becomes kind of routine. You can just play around. The domain of mathematics, after a while, you catch hold of the domain, you can just play around shifting the operator and all this. Initially, it might look bit tricky, but it kind of becomes very routine afterwards. And here, this is scalar, pi n times this, pi n inner product to this means last component, and pi n inner product to this means again last component. The two last components are same. So, a square of that. And last component is E p b n minus 1 square. I can put again I am repeating this sentence. I can put n minus 1 here as a subscript, but I am dropping it square So, let us try to write the algorithm then. Algorithm is not so easy. Initial condition, there is n equal to 0, and then for n equal to, we start at n equal to 0, right, x 0, so it should be n less than 0, is not it? It should be n less than 0, I think. We will see, because x of 0 is a valid data, it is not part of initial condition, x of 0. So, for n equal to 0 to any index, current index, anything, or you choose a very large number up to which you will do the estimation, or final. Time update is time recursion, and at each time index there is order recursion. For the 0th stage, You complete the thing for the 0 stage first. First you write something for the 0 stage and then for p is equal to 1 to something. Okay. This is the way. So, at 0 stage E you please correct me if I make mistake. You see, it's purely extempore for me. Not even a split of second. I thought about this before coming to the class. You know, just so I'm working out here. It's my workbook. Please go with me and correct. You know, wherever is needed. Huh? Okay, this is the thing. That is one thing. Another thing is the norm square. Sigma 0 f. What is the notation? Sigma p n, no? Yeah. This is the thing, sigma p n f square, no? That is equal to current data. Either you can write in terms of E0 or directly x square n plus lambda times old ones. So, you understand, if you know the index starts at n equal to 0, n equal to -1 is coming, that is those quantities I will pull here, I will write here, otherwise recursion cannot go on. Na? You are getting me, na? Here this recursion at n equal to 0, okay, fine, x square 0 is coming, but in this recursion see lambda into past, so immediately become -1. So, I have to provide data for -1 thing, that will be in this initial condition thing. Gamma, yeah, I forgot to mention. This order recursion, I will come to the algorithm, if not today, next day, but again this is an order recursion, you know. So, where does it start at? What is gamma 0 n? Suppose I do this algorithm, this is valid for p greater than equal to 1, suppose. P equal to 0 case, we will do separately. P equal to 0 means like if I want to find out gamma 1 n, can I write it at some kind of gamma 0 n minus, I mean this way, this kind of form. See, this algorithm gamma 1 n gives rise to gamma 2 n, gamma 2 n, gamma 3 n, gamma 3 n, gamma 4 n, all that. Fine. P equal to 1, if p equal to 0, there is a problem, because P 1, I am already starting at 1 and going up to 0, you know, there is no the way I did, you know, that first stage of the lattice separate, the same philosophy will apply here to be correct. So, that is what I am saying, so this recursion I did for p greater than equal to 1. So, from 1 to 2, 2 to 3, 3 to 4, like that. For p equal to 0 case, we will work out separately. Suppose I want to find out the recursion for gamma 1 n. What is gamma 1 n? By this formula, p 1, comma 1, comma n, sorry, norm square. P 1, comma 1 means Z inverse x n, only Z inverse x n. On that pi n is to be projected, taking the error. So, this is, you write inner product of this with itself, take out the operator from the last guy, same way as here, and P 1 1 n, P 1 comma 1 comma n perpendicular pi n, comma just pi n, P 1 comma 1 comma n perpendicular pi n, you just do directly. What is the meaning of this? Pi n projected on Z inverse x n and taking the error. That is error. So, pi n minus pi n minus z inverse x n pi n divided by norm square of z inverse x n, which is sigma 0 into z inverse x n. This is what you substitute here. Pi n with pi n, inner product is 1. Pi n with pi n is 1. So, 1 minus is very much like this. Again z inverse x n with pi n. So, this is a scalar. Same thing, na? This component, this much was scalar, so only between the two. Similarly, this much is a scalar only between this and pi n. So, that is the repetition of this inner product, this and the same inner product, square of that. And what is that? Last component of x n minus, x n minus 1, last component, that is x n minus 1, square of that. Okay. This vector, last component. Again same thing, this vector multiplied by pi n means last component of this. Same thing squared up. So, x square divided by sigma 0. So, you see, you now compare the two formula, general formula and the special case. This quantity and this quantity are same, you agree? This quantity is the same, the bottom matching. So, gamma 0 n, I find out gamma 0 n to be like this 1. So, gamma 0 is 1. So, here in that algorithm, where is the algorithm? Gamma 0 n is always 1 at any index n independent of n. Okay. Then by the way, as I told you here, it takes sigma 0 f n minus 1 square, but there is no data before n equal to 0. So, those norms are 0. So, why only for 0th order is true for all orders. This sigma, you ask me, sigma?
For other orders, sigma will update in the same way.
Yeah, but I am talking about index minus 1. Though, to be frank, in the lattice algorithm, when it comes to forward prediction error, this sigma f, I do not need this at any stage other than 0. Because always I will come across sigma 0 f n square. Only in the first stage while updating this guy comes. But when you order update the norm square sigma 0 f n whole square, n does not become n minus 1. Problem comes with the backward prediction. There I told you one layer of memory is required to store the previous, the norm square of EP b n minus 1 vector. That memory is required. Da? That is why that is for all orders. Do you remember that is for all orders? We need that. If we need that here also for all orders. This is a very crucial quantity, mind you. So, this amounts to, this says that you need to store, isn't it? You need to store, because at nth index you need the data used obtained at n minus 1th index, but there is not strictly for backward prediction error pth order at any general p. So, all for all the p this needs to be provided. So, therefore, in that initial condition I should have data for that backward prediction error norm square for all order at index n equal to minus 1, because to for doing computation n equal to 0 also I need that data, right. But for forward prediction error I need only for the 0th order. In all other computation from sigma p f n square you get sigma p plus 1 f n square, n does not become n plus 1 or n does not become n minus 1 and all that in all those relations. N minus 1 thing come only in context with backward prediction error. If you check all our relations we derived, you will see there is a, and that is where problem comes, and what problem we discussed once, and that is the moment has come to tackle that problem, the problem of linear dependence. So, here sigma 0 no problem with this, sigma 0 minus 1 f square equal to 0. I will come to this row, I will fill up more things as and when as I find that okay, I will need, I will come back to that. Okay. So, it is not that this is done, even here I am not sure, but now it is for I am in the general index n, for any index n 0th stage, lattice 0th stage E 0 f n, E 0 b n, I know what they are, corresponding norm square I know, this also equal to sigma 0 n b square, this we have verified, and gamma 0 n equal to 1. Now, for equal to 1 2 some name you give, if final is the time index, order for each index I am doing order update. So, capital P is a projection operator, you give a name order, okay. It could be 20, it could be 30, up to which order you can want to go to. At each stage, you first need delta. Using delta update. So, first we know the formula delta p n. So, that means is equal to lambda delta was there, isn't it, delta p n minus 1 plus this formula that we derived. Where has that page gone? I know, but what is that page? This is the thing, lambda into delta p n, then so p equal to 1, we call it p equal to 0, because that will be we are in the 0th stage of the lattice, and then first stage, second stage, delta 0 n, delta 0 n minus 1, and then E 0 f n using the given E 0 f n, E 0 b n minus 1, E 0 b n minus 1 have to give here, you remember. So, that means E 0 b, why only 0? This will come at any p. So, E p n minus 1, it should be written for all p from 1 to order this is equal to, you know, when you write the program, but I am not writing it. When I put E p means for all p from 1 to order. For, so, E p b n minus 1, that is minus 1 0. You understand how I am proceeding? The way I write algorithm, immediately I find okay, wherever I have to provide data for n minus 1th index, I am going back there and writing the data, because I have not marked up the algorithm, you know. So, I have to reconstruct by this back and forth we are doing. Okay. So, at 0th stage, say I found out the multiplier value from its past value. So, I have to store this also. This also minus 1 will be 0 for all orders, my God. Okay. You remember, no? I need to give past value, that is for all order, not any, not just 0th stage, not for p equal to 0, for any p. So, if I know that, I know these two values, So, I get this fine. Using this, minus by sigma p this was n, right, n or n minus 1, this was n minus 1, n minus 1. Okay. This for p equal to 0, I already know the norm square, they are already given here. Delta has been obtained here first, delta 0 n obtained here. These prediction errors are given to me either directly or through their past values. So, I know these two. I found out this, but I need to now update the norm square and I need to update gamma. Gamma update formula needs what? This. No, where is gamma update formula? Reverse side. Gamma update formula gamma can be updated here. Sigma values are to be updated. This will be worked out, should not cause any problem here. This is the simplest of all relation. You understand pretty well that whatever I need the formula, they are already obtained. Deltas are obtained, all this lower order the norms variances are obtained and all, okay. And this way you go around. Problem is here, this guy is coming here, here, anywhere else here, okay. So, I have to give value for this for n minus 1th index. What is this guy? This guy is the norm square of the backward prediction error vector. What is the backward prediction error vector? Z inverse p x n projected on the space spanned by x n up to Z inverse p minus 1 x n. So, if that Z inverse p x n is lying in the space spanned by x n to Z inverse p minus 1 x n, then that projection error will be 0 and there will be division by 0. You remember I did it elaborately that time, and when does it happen? Number of row less than number of column. In fact, all 0 column or more than one all 0 columns appear in the very initial stages. Okay. To take care of that, so till that our index n increases beyond that number of row columns, number of columns will be order plus 1 whatever. Okay. This problem will continue. To avoid that, what we do, and we verify, I will come back to this issue, there is no time, that instead of giving this error as 0, sigma p minus 1 b square, instead of giving it 0, we gave it a very small quantity delta. Delta greater than 0, but approximately 0, very close, 0.00001 or something like that. Effect of that you try to investigate, and in next class I will take up. Next class what I will go for, actually I have to do justice to the title given. Now, there is another category of RLS lattice filter called QR. Q1 means Q is a unitary matrix or is a upper triangular matrix. Given a data matrix, say that UN as I consider or matrix with columns x n, z inverse x n, z inverse 2 x n, dot 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 z inverse p x n. You have a column matrix like that. At any index, you have got a big rectangular matrix. That matrix can be written as product of one matrix Q, which is a rectangular matrix, but columns are mutually orthogonal or orthonormal. So, it is actually unitary matrix times a upper triangular matrix. And as time index changes, elements of the Q and R can be updated by simple formula. There are various ways of doing it. One is by Gram-Schmidt orthogonalization, we will see that it results in that. Another is by Given's rotation. Have you come across this term, Given's rotation? We will see it is a beautiful thing, Given's rotation. It is very picturesque actually. The way rotation steps take place is beautiful. So, by Given's rotation, we will consider this, that given a data matrix, we will basically get its equivalent upper triangular form. And then getting those linear combiner coefficients will be very simple in solving an upper triangular matrix, and it will basically be done through a systolic array. Systolic array, those who know, I mean, some people have done my course earlier, so they know, but those who do not know, it is an array, pipeline array of processors arranged in a very, regular manner, and overall computation is very fast. It is totally pipeline. So, we will see that from the next class. This just I will take up in the next class about this delta issue. Okay, what I will do, I will take out this paper today, so that I do not have to rewrite the entire algorithm. Okay, I will bring it back. Just delta issue, you also think over, you will see that delta will prevent the division by 0. Delta will always make sure that even if there is an all 0 column, its norm square of the corresponding error vector is not 0, but at least delta is delta. This we verify. Okay, thank you very much. No attendance.